Okay, morning everyone. Thank you for joining us in RC design class on a Monday. Today will probably be the last lecture of the whole course. We're going to talk about the column a little bit more on how to calculate the forces and the bending moment with respect to different axes today. And today is more like a fill in the blank type of example. What I mean by that, I will give you the steps and questions. We may have to ask you to help fill in the numbers to get the final answers. So to speak, it's more of a practice for you as well. All right. So this will be the last lecture, and Wednesday we will do a review lecture of talking about what will be on the exam, and also on Wednesday we'll be doing a on in class evaluation, filling out survey type of thing on Wednesday. So we'll not have lectures on Thursday. Now I have several students asking me about the final exam arrangement. So far, it is still scheduled from 2 to 4 p.m. on a Friday, the final exam day. We have few students that have to do a different time and working with them, but be aware that if you do individual arrangement with me, you need to let me know like right now so we can start doing the arrangement. And your exam will be different from everybody else in the class. So you have to anticipate certain level of difficulty changes or differences if you want to make such request. Okay. All right. So I'm going to pause here. Any questions? Any problems, questions? Okay, before I forgot, the design lab, which is the beam design, right? Shear and flexure, that is due the day before the finals, right? It's a midnight. Well, actually, in the midnight that final day. Okay, so make sure you do a proper job of reporting. Okay, clearly identify your analysis rationale, the details and the steps you take, and also attach your Excel sheet. Either you just use Excel sheet I offer, which is totally fine, or you actually program your own Excel sheet. Just please attach that so I can see that from the report. Okay. All right. So that's about the design lab. And uh, sorry, folks. Okay, here we go. And one more thing about the grading. I'm finishing up the grading homeworks this week. And by Thursday, you should see the older grades except the design lab. And we'll not know the design lab until the exam's over. Okay. But like I said again, the top 2 teams from design lab will get extra points. Okay. All right. Any other question for me, folks, about the finals and the lab and everything else? Anything? All right. Okay. If nothing else, we're going to continue with the column. I will leave one more homework after column is finished today, but this homework is not to be turned in, so you don't have to turn in for grading for the last homework. But if you have a question on last homework, however, you can still email me, and I will still hold office hours next week, before the finals. So if any question, just email me. I would love to set up individual time to communicate that with you. Okay. All right. Without further ado, let's continue on the column. All right. So before I start, all right, I want to share with you a unique problem that has appeared about 2 years back in the final exam. Okay, so the final exam read like this. A column has a section. So today was more about examples. A column have a section shown below, okay? And I will show you that it is a very typical rectangular section, okay? And the concrete that to be used for this section is prime C equal to 5 KSI, okay? Then the grade 60 steel, meaning yield strength of the steel 60 KSI, okay? And the concrete cover, it tells you that the concrete cover is 2.5 inch, okay? And this is not only from the top and bottom, but also for the side. So for the side and bottom, right? All directions, concrete cover is 2.5 inches. Okay, so the section looks like this, right? A rectangular section, old-fashioned, nothing particular. Interesting. And the width is 12 inch. Okay. Height is 20 inch. Okay. Now we have stirrups, all right, and the stirrups go through it. And I should be careful because this is a column, so I call them ties, right? Ties because they're closed loop stirrups. So they're ties. They're ties. And I have 4 bars at the corners, 4 bars at the corners. And this is clear that we tells you that the tie is number 3. Number 3. Okay, so you don't have to guess. You don't have to worry about the diameter. It's number 3, so told you already, right? So the cover that it was mentioned in the example is 2.5 inch from the side to the center of the longitudinal rebar. The center of longitudinal rebar. Okay. Okay. All right. So here we say that this is 4 number 10 bars. Okay. A little bit different. Number 10 bars. Okay. And now we have eccentricity, right? We have eccentricity, but we don't know that yet, right? Now here, I'm going to introduce another new thing, which is axis 11 and axis 22. So this axis 1122 is same as x axis and y axis we talked about last lecture. All right, but you see that have 2 axes, right? So immediately you have alert sounding in your mind as 2 axes, okay? Now which one is strong axis? So before you do anything, label it out. 1 is the strong axis. Now why is that? Because 1 is perpendicular to the height direction, right? And when we talk about the moment of inertia, 1/12 bh cube. So 1 is the strong axis. So 2 is the weak axis. 2 is the weak axis. So you know that, right? You know that already. Okay. Now, given all this, now the first question, so if I call this problem 1, so 1A, oh, let me switch color. 1A is asking you, what is the design? What is the design resistance? Okay, design resistance. And when we talk about design resistance, right? And we have to be specific for what? For what condition, right? So for pure axial loading condition. Okay, pure axial loading condition. Now, what does pure axial loading mean, right? Pure axial loading means that on the, and this is me contemplating, pretending I'm the student taking the exam. This is axial force, and this is bending moment. To recall what we talked about last time, and this is the curve, right? And axial loading is right here, P naught right here, right? And you saw this word design resistance. So meaning we're not looking for just P naught. We're looking for phi P naught. There's a design factor here, phi. Okay. Now we'll talk about this in detail, but you know that since it is pure compression, this compressive member, so phi should equal to 0.65. Okay. Phi should equal to 0.65. All right. But let's continue, right? So that's number 1A. Just want to find out the pure axial loading condition. All right. And 1B is what are the design resistance? What are the design resistance? Okay. Now, when we talk about this, we mean phi Pn, phi Mn, okay? Phi Pn, phi Mn for balanced, okay? For balanced, okay? Failure. All right. With respect to, here we go, right? With respect to 1 axis, okay? With respect to 1 axis. Oops. So here we have to careful. We have to be careful. This is talking about with respect to strong axis, right? Now going on, and again, I want to label that. So at 1B, we're talking about is right here at the balanced point. This is 1A, and that is 1B. Okay. Now 1C, okay, same thing, right? So blah 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 blah. Phi Mn, phi Pn, same thing for what condition? For zero tension. Okay, zero tension. Okay, point. Subjective, so zero tension point with respect to 2 axis. All right, so it changes now. Okay, was originally with respect to the strong axis. Now it is with respect to the weak axis. Okay, all right, so that's 1C. Okay, now one more thing here, 1D. Okay, so if the compressive zone, okay, if the compressive zone okay, is 9 inches. Okay, and this is with respect. This is with respect to the strong axis, 1 axis. Okay, now what are the phi PN, phi MN? Okay, with sorry, what is this? Of course, with respect. My morning write up is horrible. With respect to 1 axis. Okay, now what does it mean again? So this means if my eccentricity, so I'm just gonna again use my blue color indicating I'm just thinking. So this is my section and 1 axis is right here. And so the compressive zone is 9 inches. Means that if I draw my strain diagram, okay, if I draw my strain diagram, the compressive zone here is 9 inches. C is 9 inches. Okay, and for that, we're asking is, what about my phi PN and what about my phi MN? Okay, so that's 1D. All right, so this is a typical final exam problem on the column. Okay, so you have 1, 2, 3, 4 problems. Okay, now a little bit different is that 1C is talking about with respect to 2 axis, which is a little bit different, So you have to go through some hoops, okay, to get it around it, okay, get around it. All right, so let's talk about how we're going to solve this problem. All right, so this is how we're going to do it. Now, first of all, solve, right? Solve the problem, right? So first thing first, before I start everything, right? I thought about maybe I should start looking at number 10 bars. Okay, why is that? It's different from number 9 bars. Okay, so from the table you have on the bars, right? We know that number 10 was a dB of 10/8 inches. Okay, and with a cross-section area of AS bar per bar, that is 1.27 inch squared. Okay, so these are 2 numbers I'm going to use often during the problem solution part. Okay, so you want to just put it out there. Okay, now 1A, right? 1A. So 1A is talk about for pure axial loading, right? For pure axial loading, that means pure compression. So immediately I know that since it's pure compression, so phi should equal to 0.65. Okay, phi should equal to 0.65, no doubt, right? And then we recall the axial loading equation P0, and that is 2 parts. One is K3 F prime C A, and this is concrete C plus another steel, which is Fy AST. Fi AST. Okay, now considering this, K3 is equal to 0.85. Okay, so this is a constant. If you forgot where this is coming from, go back to the previous lectures, but we just show you that K3 is 0.85 without any derivations. Okay, now F prime C in this case is 5 KSI, so we're just gonna label here, right? So AC, which is the concrete part, equal to the total cross-section area minus the area of steel. So AG minus AST. Now AG is BH, right? Minus AST is 4, number 10 bars, so 4 multiplied 1.27 inch squared. So B is 12, H is 20. So this is what the total area of AC is, okay? I'm going to actually leave this out so you can fill in. Okay, so kind of exercise, follow it through. All right. So now you got AC, right? AST is what? AST is just the bar, right? So AST equal to 4 multiplied by 1.27 inch squared. Okay. Again, I'll leave it out for you to fill it in. Okay. All right, so with this, I know the concrete area, I know the area for steel, right? So I'm starting computing my phi Pn or phi P0 in this case, okay? So Pn equal to P naught, that's pure compression, okay? And that is the equation. So simply just put the phi in as 0.65 multiplied by the whole thing, which is this whole thing. So K3 F prime C AC plus Fy Fy don't like this Fy AST, and that is the total design resistance, right? So you bring the number in, so phi Pn equal to 0.65 multiply inside K3 0.85 multiply F prime C 5 KSI. AC, you calculate some number from here, right? AC, okay, plus FYAT 60 KSI multiply AST 1.27 inch squared multiply 4 bars. Okay, so that is what we have here. That is what we have here. So let me just get this question mark out of the way because I can probably write this way. Folks, sorry about that. You might have to change it a little bit. So this is 12, 20 minus 4 multiplied by 1.27 inch squared, bracket outside minus that. Okay. All right. So be careful on the unit. We have KSI, we have inches. KSI, inches. So the unit comes out to be kips. Okay. And again, I want you to just follow through the process and calculate the number out for yourself. Okay. So that is the total pure axial loading for case number 1. So 1A done, right? Not too bad, right? Not too bad. So 1B. 1B again is 1 axis. Be careful. This has to come out front, okay? 1 axis. And this balanced failure, okay? Balanced failure. So these has to be the front. You know that, balanced failure. Again, let me take a look at the diagram, right? We know that from this right here, the axial force versus bending moment loading, and the curve looks like this and turns back here. Okay, so at the balanced failure, we know that is right here at the knob, right, and here at the pick here. And then we say that the strain at the balanced failure equal to 0 point yielding strain for grade 60, 0.00207. That is the input. That is the given information. Okay, given information. So with this, let's take a look at the strain diagram. Let's take a look at the strain diagram, right? So the strain diagram shows that I have a balanced failure, meaning my epsilon Cu in compressive concrete 0.003, and my strain is still epsilon S equal to 0.00207. Okay, now given this, I need to find my actual compressive zone size C, and I need to find out the rest of the things. Okay, so now first thing first, right? What is actual compressive zone C here? C equal to D, which is the depth of the bar, right? Depth multiplied by the strain, which is epsilon Cu divided by epsilon Cu plus epsilon S, epsilon S. Okay, so C now equal to the numbers, right? D, what is D? D is the height H minus the concrete cover, right? 2.5. So let me just use numbers here. So H is 20 minus 2.5 inches. That is the depth. And multiply epsilon Cu equal to 0.003 divided by 0.003 plus the yield strain, which is 0.00207. Okay, all right. So now what is C? Right? Calculate it out. And just to help you out, this is 10.3 inches. But anyway, run a calculation, right? Go through that yourself. Okay. All right. So with that, C is given, the actual compressive zone is given. What is my A, right? What is my A effective compressive zone? A is beta 1, C, that is 0.85 C. And you can get A. Okay. Run the number, get the actual compressive, effective compressive zone A. Okay, now be careful. This is balanced failure. So when that happens, I know that my tensile stress in the bars equal to the yield strength of the steel, which is Fs equal to Fy, no problem. But I don't know is what is my compressive stress in the bar Fs prime. Now Fs prime should equal to the Young's modulus Es multiplied by the strain in the compressive bar. And the strain in the compressive bar is epsilon Cu multiplied by C minus ds prime divided by C and bracket outside square root square end of it, square parenthesis out of it, right? And then bring the number in Fs prime equal to Young's modulus for steel 29,000 KSI, okay? Strain for concrete 0.003 and C some number, right? So I know this, so just 10.3 inches minus ds prime, which is the concrete cover 2.5 inch divided by 10.3 inches, bracket outside and bracket outside. Okay, again, you will calculate this number out, but you find this number, I can tell you right now, is 65.9 KSI, which is slightly bigger than the yield strength, slightly bigger than the yield strength. Okay, but what did we say last lecture? Because we have ties in the column, right? So these bars in compression, steel bars in compression is allowed to yield, and so we have Fs prime capped to be 60 KSI, 60 KSI. Okay, all right. I already gave you some number, but please go through them. Okay, fill in the blank so you know what they are. Okay, you know what they are. Okay, now at this point, right, we should have several things now. We have the effective compressor zone A, meaning we can get the compression force for concrete CC. Now we have Fs equal to Fy, meaning we can get the tension force from the steel. And now we also have Fs prime, which is compressive stress, meaning we can get Cs, which is the compression force from the reinforcement as well. Okay, so in this case, now CC would equal to 0.85 F prime C AB, right? So 0.85 in front of F prime C is what concrete? 5 KSI concrete. And A is some number we calculate out, right? So 0.85 multiplied by 10.3, and that is A. 10.3 is C, by the way, right? And width is 12 inches. Width is 12 inches. So you got the compression force CC. Now, what about CS? CS should equal to the area of steel in compression AS prime multiplied by the Fs prime stress in the steel minus, don't forget this part, 0.85 F prime C by filling into the missing holes of the concrete, right? So bring number AS prime, I have two number 10 bars in compression, two number 10 bars in compression. Fs prime equal to 60 KSI, and then minus a 0.85 F prime C, which is 5 KSI. Okay, and then please calculate out, right? So what is my compression force from the steel? Now tension force easy, right? TS equal to ASFY, ASFY. Now AS tension, right? So how much bars in tension? So how much bars in tension? 1 multiplied by 2.7 inch squared, right? So not 1, 2. 2 bars in tension, right? 2 bars in tension. 2 multiply 2.7, my brain. 1.27 inch squared area in tension, and then multiply 60 KSI. Yes, this makes sense. Okay, all right. So now that is the internal forces. Okay, but we're not done yet, right? So this is internal forces. How about the design resistance, right? So we're talking about Pn, which is the total axial force, right? That should equal to Cc plus Cs minus Ts. Now, why we use minus? Because it is at the balance failure, right? Balance failure, so tension still is there. There's still tension, okay? So please bring the number and plug them in, okay? How about the moment? So Mn, which equal to what? Pn multiplied by eccentricity. Now we don't know the eccentricity yet, but we do know is that this equal to compression Cc multiplied by distance between the total compression to the center of the section. Now the centroid, okay, be careful. Now centroid, okay, it's the center of the section. So half h minus half a, half h minus half a plus cs, right, compression force, and half h minus ds prime, okay, ds prime, and then plus ts, tension force, multiplied d minus half h, d minus half h. Okay, so again, please plug in the number, right? So for your all you need right here should be equal to h is 20 inches. Don't forget that is height, ds prime equal to 2.5 inch, which is the concrete cover. Okay, just walk through this. Okay, walk through this. So now you got a VPN, VMN. Okay, now the question is, what about phi? What is phi, right? Now this is balance failure, right, Bob? So what is phi? You have to calculate it out, should you? Well, let's take a look, right? What is phi anyway? So axial force P is here, bending moment is here. Excuse me for a second, I have some noise here. Let me just give me 1 second to close the door. All right, I'm back. Sorry about that. So again, PMN, actually PM curve looks like this. Looks like this. And we have axial forces here. Remember, this is point A, zero tension point B, and balance failure C, tension control D, and pure bending moment E, right? And if you recall, we actually divide them in terms of zones, right? So we say this is A to C is in compression, right? Is in compression. C to D is in transition. D to E is in tension controlled, right? So 1, 2, 3. So where is C at? C is right here, right? C is at the borderline between 1 and 2. And for 1, phi equal to 0.65. For 2, phi equal to some equation as a strain of the steel, epsilon T. And 3, phi equal to 0.9. So since C is at the borderline between 1 and 2, so phi naturally is still equal to 0.65. Okay, 0.65. Okay. All right, so that is phi. So plug the number, please, and now you should get the design resistance for the balance failure with respect to strong axis 1, with respect to strong axis 1. Okay, all right, so much for the strong axis. How about 1C, right? And be careful if we go back, and I don't bother to go back, but the key parameter, let me just put it out here for you, is that it is with respect to the weak axis, which means 2 axis. Okay, and this is also about zero tension point, zero tension point. Okay, so in your head, first thing to do is to flip the section, flip the section. So originally the section looks like this, right? Right. So this is 1, and this is 2. Okay. Now some of you may be very good at geometry. For people like me, folks like me, I have trouble understanding geometry. So in my head, I'm just gonna flip it. I'm just gonna flip it. So how to flip it? Here in the software is even easier, right? So just flip it like this. Okay, flip it like this. And make it larger so I can see better, right? So flip it like this. So when I flip it, right, this become again 1. Just want to write it in upward direction. Then this is 2. Okay, this is 1, and this is 2. Okay, all right. So this is the section. This is the section. Okay, now with this, we can put the differences, right? We can put the differences in terms of strain now. But before I do that, I just want to label out where the bar is at. We just want to label out where the bar is. So the bar is still here, here, here. Okay, bar is still here, here, this point, and these are the ties. These are the ties. Okay, and now the concrete cover is right here, somewhere right here. 2.5 inches. Concrete cover right here, 2.5 inches. Okay, and these are the 4 number 10 bars. Number 10 bars. Oops, 4 number 10 bars. Okay, now this is zero tension. Remember, zero tension. So now I need to draw my strain diagram, and I don't like this. Let me get this color back. So the strain in terms of compression is concrete epsilon Cu still 0.003. 0.003. Okay, now in terms of zero tension, right? I mean, the entire section is going to see compression. So the very bottom here is going to be zero. Very bottom here is going to be zero. So the level of steel right here at this point here, this is epsilon s. And that is something we don't know. That is something we don't know. But we do know that this is the depth. Okay, let me put a 2 mark here, 2 mark here, so you know this is not the depth of 1 anymore. It is not the depth of 1 anymore. Now, in case you are not clear, and this is the width of B, not the H anymore. Okay, now line up with the strain compressive side of it. Now, this entire section is compression, so that is still the compressive strain epsilon s, and this is ds prime, ds prime. Okay, so I want to analyze the stresses now given the strain diagram, right? So what my stress analysis tells me is that my strain in tension, supposedly, but now it's in compression, okay, you can actually see it, divided by D, 2 should equal to the triangle, similar triangle epsilon Cu divided by B, right? So now epsilon s, which is in compression, equal to a d22 divided by b and multiplied by epsilon cu. Bring the number, right? So epsilon s equal to d22. What is d22? B minus 2.5 inch. Okay, and the b width is 12 inches. Okay, and divided by b, another b here, 12 inches, multiply 0.003. Multiply 0.003. Okay. All right, so again, please fill out this number here, okay? Might be a little bit annoying, but I want you to guys actually walk through it, not just copy what I wrote here, okay? So this is on the bottom here, okay? Supposedly in tension, but you can tell that it is gonna be in compression. It's gonna be in compression. So this whole thing is gonna be in terms of negative, sign because it's in compression, okay? Not tension side. Anyway, so epsilon s prime divided by d minus ds prime, d minus ds prime, that equal to epsilon cu divided by b, epsilon cu divided by b, and that gives me that epsilon s prime and equal to d minus ds prime divided by b with n multiplied by epsilon cu. Okay, now again, this d is d22, right? D22, so that is b, which is 12-inch minus 2.5 inch, which is d22 minus ds prime 2.5 inch divided by b, which is 12-inch, and multiplied by 0.003. All right, and now I got this number to be a equal to a beta 1 multiplied by b, beta 1 multiplied by b. Okay. All right, so this is the actual compressive zone, okay? Actual compressive zone. So, oops, 1 second, okay. Once I have that, this is actual compressive zone A, I can start calculate my internal forces, right? And don't forget, beta 1 is still 0. Oh, wait a minute. I think I messed up the beta 1 because it's no longer 4 KSI, isn't it? So I have to start using that equation. Okay, so folks, I have to make a correction here. Where is it? Did I make a mistake at? So change here. Okay, this is not 0.85 anymore. Make sure you use the correct beta 1. Okay, so beta 1 is 0.9 and 0.65. So 485. 65, got it wrong the other way. So maybe 0.85 for KSI and go on. And this is 6 KSI, I believe. And this is 6.5. Apologize for that. And this is 8.5. Okay. Okay. Gotta do the linear interpolation. I have to do the linear, I forgot about it. Okay. So you actually have to do 5 KSI, which is right here. So I'm use a different color. And again, I want you to go through this 5 KSI, and then this is what it is. Okay, find beta 1. Find beta 1. All right. Okay. All right, so I think I made a mistake here. Where else I made a mistake is that I think that's it. So change this to be the correct beta 1, okay? Change this to be the correct beta 1, okay? And B is 12-inch, you know that, all right? Okay, so this is the actual compressor zone A, right? And with this, I can proceed. I say, you know what? I have all the stresses I need, all the stresses I need. Okay, so with the stress, I want to calculate my internal forces. So the tension Ts would equal to ES multiplied by epsilon S, where ES is Young's modulus 29,000 KSI, okay? And epsilon S equal to a D over B, okay, which is right here, okay? So I'm gonna save you the hustle, just write out epsilon S, you need to find out number yourself, and that is the tension force, okay? Now, you know that at this point, my real tension is in terms of compression, right? My tension is in terms of compression, because this epsilon S will have a negative sign in front of it, negative sign in front of it. Okay. Now the compression force CS in steel would be ES multiplied by epsilon S prime, which is 29,000 KSI again, multiplied by epsilon S prime. And this is in compression, so I don't have to worry about the sign for the compressive steel. Now for the concrete CC, that is equal to 0.85 F prime C, 0.85 prime C, beta 1, BH. Okay, so you know the rest of the number, just have to be careful on the beta 1, okay? Just have to be careful on the beta 1, all right? Now, when you calculate out, you can proceed to find out the PN, which is the axial force, that is CS plus CC minus TS. But this is zero tension point, right? So the negative sign you carry it within TS will be converted back here, and then this will turn into a plus. This will turn into a plus. Okay, so just be careful when you do that, all right? And you can give me the number on the axial forces. Now the bending moment. Bending moment is the same thing before, right? And we'll have the same equation, CC multiplied by half H, but be careful. This is with respect to 2 axis. So the H have to flip and into B and divided by 2 minus A divided by 2. Okay, so B now, no longer H anymore. Okay, and this is CS prime multiplied by the B over 2 minus DS prime, and this is all 2.5 inches in case you forgot, right? And then plus a TS multiplied by what? What the distance is D, and be careful this D, right? It's no longer the 1 axis D, is the D with respect to 2 axis. D22 minus B divided by 2 bracket outside. So this whole thing is the moment, okay? All right, one more thing. Now you think of it, the tension is no longer in tension, right? The tension is actually in terms of compression. Tensions in terms of compression. So when I sum the moment, right, I want to show you the strain diagram again, just in case you forgot, right? So this is the strain diagram, and this is where the epsilon Cu is at. So let's take a look at these forces, right? The compression force Cc is right here, and the steel is right here, somewhere here, and this is CS, well, compression. So now I have, supposedly I have tension, but instead I have a negative tension, right? So it's in terms of compression. Now, when I sum the moment, I suppose just do the 3 forces, right? However, be careful. When we say we sum the moment, we're actually summing the moment. 2 complications. One is that this is no longer H, this is B. Second is that when I sum the moment, they are in different sign. And remember, we say that a TS has a negative sign carried in it. So this negative sign will turn into a plus, and this plus sign will turn into a negative sign. Okay, all right. So I don't want to muddy the water further. Carry out this calculation, plug the numbers, okay? If you have a question, come back to me, okay? Question, come back to me. All right, so this is 1C. This is 1C, okay? Last one, 1D, okay? 1D. Again, 1D is with respect to what? 1D is with respect to 1, axis. Okay, so that is easy, right? 1, axis. I don't have to worry about it. Okay, so but don't have to flip the section, don't have to do anything, right? So it's still the same rectangular section we're looking at from above, and this is 1, axis. Okay, now the question tells us that the compressive zone is 9 inches. Okay, it forces you to do that. It forces you to do that. So how do we deal with this? We haven't done this before, right? And if you remember in the previous lecture last time, we said that we want to set up a compressive zone so big that is even larger than the height itself. Remember? We said that, right? But for this case, when C equal to 9 inches, we have to do the strain diagram again. We have to do the strain diagram again. This is where the C is at. C is 9 inches. Okay. Now, when C is 9 inches, right, we first thing need to find out is what is the effective compressive zone A. So that is beta 1 C. Now, I cannot use 0.85 anymore because it's no longer 4 KSI concrete, right? So got to be careful, find out the interpolation of it, right? But I can find my effective compressive zone A. Once I find that the compression force from the concrete CC would equal to 0.85 F prime C AB. AB. Okay, so you carry out the calculation. The only thing you need to be careful is B is equal to 12 inch. B equal to a 12 inch. Okay, right? So no longer the flipped section, right? This is still the old-fashioned section, right? So you can calculate the compression force of CC. Once you have that, the compressive stress in the reinforcement Fs prime would equal to ES. Find out the strain in compressive reinforcement, and that is C minus ds prime divided by C multiplied by epsilon Cu. So this number here is 29,000 KSI. Okay, C is what? 9 inches. Told you from the problem, right? DS 2.5 inch, and C again 9 inches and 0.003 from the concrete compressive failure. Okay, over and there. So now we need to know what about this compressive stress Fs prime. Okay, and also check if it is bigger than yield strength of 60 KSI or not. If so, okay, we need to set Fs prime equal to 60 KSI. All right. Okay, so that is that. Now, epsilon CS, which is the stress in in tension reinforcement, right, should equal to a D minus C divided by C multiplied by epsilon Cu. And that is D. What is D now? 20 inch, which is H minus 2.5 inch, right? That is the depth. And if you really want to be clear, that is the depth in the 1, axis. Okay, and this is minus 9 inches, which is given, divided by 9 inches multiplied by 0.003. So I have this strain is in tension, okay, in tension, positive now, okay, in tension, and calculate this out, please. Calculate this out, please. Okay, so I have my strain in tension, right? I have my strain in tension, and I calculate out the strain in tension, right? But I need to find out whether this is bigger than the yield strain of 0.00207 or not. Okay, I need to find out whether it is 0.00207 or not. Okay, all right. So lo and behold, tell you a secret. The question, I mean, the answer to this question is yes. Okay, still yielded. Meaning epsilon s is indeed larger than 0.00207. But please calculate out yourself. Find out if this is true. Okay, all right. So now take a look, right? So what we did, we find out the compressive stress in the steel, find out the tensile stress in the stress in the tension, right? And we checked whether the strain in the tension side is bigger than the yield strain or not. Okay, and I told you already, leaked out the results already. It is yielding, but you find out that it is only slightly bigger than that, but still smaller than 0.005, which is tension control limit. Okay, you find out that is in between. Now, what does it mean by that? It means that in terms of axial force, in terms of axial force versus bending moment diagram, and I have a point, and again, let me use this curve here. I have a point that I don't like this. I should draw it bigger. Okay. Okay, this is more like it. So I have a point that it is no longer C, because C here is a yield strength. It is no longer D, because D here is tension control. It is somewhere in the middle. It is somewhere in the middle here. Okay. So the question is, how do I compute phi? How do I compute phi? Okay. So you remember when we compute phi, we also have a little diagram here, right? So if phi is not yielding, which means less than the yield strength 0.00207 or 0.005 yielded tension control, there are two limits, right? One is phi equal to 0.65 and the other is phi equal to 0.9. And in between, what you do linear transition. In between, you do linear transition, right? So we have a strength somewhere here. Okay, so this is what is the phi is at. So you got to do the linear interpolation to find out phi. Okay, find out phi. After you find out phi, things are easier, right? Why is that? It's because Pn would equal to Cc plus Cs minus Ts. Now you don't have to worry about the sign because tension is indeed tension, right? And how about Mn? Mn equal to Cc half H minus half A, remember, plus blah, 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 right? We have a long equation. You can use the equation before. And since we don't have to flip the section because this is one axis, so the height is still the height H, okay? All right. Okay, once you have that, plug the phi you find out from previous step, phi Pn, phi Mn, okay? All right, okay. All right, so this is the entire problem, this entire problem. Okay, now this will be our last quiz. This will be our last quiz, quiz 10. Okay, quiz 10 is that you just have to give me a final number on phi mn 1a. Just write down in the text like this. Phi mn is what? 1b, phi mn, phi pn, phi mn what? 1c, phi pn, phi mn are what numbers? And 1D, phi pn, phi mn is what numbers? And when you do this quiz, right, make sure that units in terms of kips for P and kips foot for moment. Kips foot for moment. Okay. All right, folks, that's it, ladies and gentlemen. This is for quiz 10. This is for quiz 10. And this wraps up the entire course. Okay. And I'm going to stop here and you're welcome to stay if any questions regarding the process. Okay. All right. Thank you. And if nothing else, I'll see you on Wednesday. All right.
So did you say we're gonna have a homework?
Yeah, we're going to have a homework today, but I'm going to post it and you don't have to turn them in. It's just for you to practice.
Is it gonna be if we turn it in, do we get points though, or?
No, you won't get points. You just need to practice. But if you have a question about this, like say you try to solve it, you have any question, email me. We can set up one-on-one and I can show you the correct answers.
All right, thank you.
Yeah, not a problem. Okay. All right, folks, we don't have a homework to turn in. I will post it, but the quiz need to be turned in, okay? The quiz, don't forget the quiz. The quiz will be turned in. Okay. All right, again, I'll be staying here. If you have any question, please let me know and we'll see you on Wednesday if not, okay?